And then we revolved it and we have this kind of three-dimensional solid, right? And we were able to figure out that the way to find the volume is to consider cylindrical disks. And if when the cylindrical disk has a certain radius and a certain height, and the height is given by the change in x, and the radius is given by the y coordinate of the specified x coordinate. So if we're given the function of the of the uh, of the line in this case, then if we know what the function is, we were able to specify what the radius is, and then we know the volume of a cylinder is pi r squared times the height. And then if we take a sum of them, a sum of these disks, right? If we would take multiple disks, we would get a better approximation to the actual volume. And the story goes that as the cylindrical disk's thickness, as they get really thinner, you would be able to add more and more disks. And if you let that the number of disks go to infinity, which would affect the thickness, making it as thin as possible, you would get the actual volume of the solid. So that's what we did last time. And we did the same thing for a region that is revolved around the y-axis, right? And very much the same way, except that now we're going to be differentiating. I mean, we're going to be integrating or summing the cylindrical disks, but they're stacked. They're sliced up horizontally and they're stacked vertically. Whereas in the other example, these disks are sliced vertically and stacked horizontally. But the idea is the same, right? And this is called the disk method. And then we were left with last time, what would happen? What would happen if we would get two curves instead, and we got a region such as this one, right? And we revolve that region around the x-axis. The difference here is that now the disks are no longer disks. They're disks that have a hollowness to them. And those disks with a hollow core, we call them washers. They're also called annular rings. So now we're going to be discussing the washer method. So today is the second. This is lecture number 22. So we're going to be talking about the washer method. So this is the example from last class. So this is uh, last example from previous lecture. Continued. So we're looking at our previous example here, and remember we were given two functions. We were given a parabolic function that was this pink one here, 1/4 x squared, and then we're given the blue one. And the blue one was y equals, well, that's way too dark. Y equals 5 minus x squared. Oh yes, Sarah, we have two quizzes next week. We have one quiz next Monday and then another one Wednesday, which will be the last day of class. Next Wednesday is our last day. And then 2 Mondays from now, yeah, 2 Mondays from now would be the final. So that's what's coming up. Again, it's a race to the finish. So, and this is really we're gonna after this topic on volumes, we're gonna do one extra thing, which is on arc length, and that's it. When will we get the grades for? So some of you have already received exam number 2. I haven't finished everyone's yet, but you'll get them as soon as possible. Yes, I'll give out an email, a mass email to all the whole class about the dates for what's to come. Okay, so don't worry. Okay. So again, we have this blue curve, this pink curve here, 1/4 x squared, and we have this blue curve here, 5 minus x squared, right? And then we figured out that the region in between was this region here. And I want to take that region and revolve it around the x-axis so that uh, I figure out what's the volume of that solid. And I think we discussed that last time, right? And we saw it also through Maple, which is a very useful tool that you all can download from CUNY email. And let me just, I'm gonna write that again. So let me share my screen. I'm gonna share the Maple applet here. So then I'm gonna put 0.25 times x squared as my, pardon me, that should be my, so f of x represents my top function here. So it's 5 minus x squared. And then I get 0.25 times x squared. And, oh, and then one extra thing is the point of intersection is extremely important. So if I were to set 5 minus x squared equal to 1/4 x squared, and if I were to solve that, uh, you can do that on your own. So what if I need to find a point of intersection. So let me revert back. Let's find the points of intersection first. So the points of intersection, that's very important to know. So we're gonna set the curves together, set them equal to one another. So I got 1/4 x squared equals 5 minus x squared. So I add x squared on both sides. And I get 5/4 x squared equals 5. So that means that x squared equals 4. So that means that x is equal to plus or minus 2. So then, so what that represents is that this coordinate here, these are going to be my integration bounds, okay? So it's going to be -2 to 2. Those are my integration bounds. So with that in mind, I know that they intersect, my x values go from -2 to 2. So then I'm going to put that, for my a value would be -2, and my b value would be +2. And so for now, I just want to see what this region looks like. So then if I display it, remember we talked about this? And let me just look at the region for now. I'm just going to look at the region. So I'm going to click region. So this is the region that we discussed, right? This is the region that we have that's shaded as a in a green, in a neon green color. So we have this is the part of the parabola here, and this is the other part of the lower parabola. And this is the region that we want to rotate or revolve around the x-axis. And then when we do so, we get this. You see that? And we get a hollowness within here, inside here. It's a hollow cone, you can think of it. Okay, and so that's what we're trying to figure out. And let's see if it works out well looking at the discs. So let's look at the discs. What do the discs look like? Do you guys see how these discs here have a hollowness inside? So they're not completely solid discs. They have discs that have a hollowness in them. And then we can increase the partition. So let's make more discs. How about if we have 10 instead? And then you see the thicknesses of these discs get thinner and thinner, so we can fit more. We can fit more of these kind of washers, as they call them. So then the more we increment, the better the approximation is. Do you guys see that? You guys how it fits better and better as I increase the number of discs? So that's the idea. And then what do we say? We're gonna make those discs infinitesimally small, meaning that we're gonna fit an infinite number of these discs. And when we do so, we get the we get the integral, which represents the exact volume. So now the question is, how do I represent this disk? So I'm gonna draw this disk, okay? Or I should call it washer. So look at one washer. What does one washer look like? It looks like this, right? Now, this here, this is the x-axis, right? And I'm taking this disk here, okay? I'm taking this guy here, and I'm making it look like the one here. And so I have this portion here. This is part of the parabola, right? And this is part of the other parabola like this, right? And so we have something that looks like this. Now, what is the radius of the bigger circle? What is that radius? So I'm gonna call this radius big. What is the radius of the bigger circle? If I were to specify this point to be, let's say, x comma I, what would be the radius of that bigger circle? It would be the y coordinate of the upper function. So it would be what? It would be, the upper function is 5 minus x squared. So this would be 5 minus xi squared, correct? And then look at the smaller one. What's the smaller radius? The smaller radius here, r small. The smaller radius would be the y coordinate associated with the smaller or the lower function, which in this case would be 1/4 x, 1/4 x sub I squared. Do you guys see that? Does everybody understand the differences between the radii of these circles? How the bigger circle is associated with the upper function and the lower radius, smaller radius is associated with the lower function. Is that clear?
Yeah, one question.
Good. Okay.
Is
So
the
that's, yeah.
just one question. Is the five is it five subtracting the 1/4, or is it just five entirely the radius?
So this is my blue function, right? This is my blue function, correct?
Yes.
Yeah. So then the upper function, right? If I were to create a washer here, if I were to slice this up, if I were to slice up this solid, the upper part is represented by this blue function here, right?
Yeah.
So that means that the radius of the bigger circle of this cylinder here, right? The bigger circle, right? That's representing the distance from the x-axis to the blue, that blue portion of the graph. And that blue portion of the graph is given by 5 minus x squared only. And then the smaller circle is represented by the radius, right? The smaller radius is represented by the y coordinate of the lower function, which is 1/4 x squared, right?
Okay, yeah, I get it now. I was thinking of it like sort of like area, how if it has a hole, you got to subtract it from like the whole thing, but it's
So
not.
you're on the right track. We are going to do that. That's exactly what we're going to do. That's exactly what we're going to do. So then we're going to find the total volume of this new washer, correct? So what's the volume of this one washer? Well, it's the volume of the bigger minus the volume of the smaller. That's it. So what's the volume of the bigger cylinder? It's going to be pi times the radius of the bigger squared times the height minus pi times r squared of the smaller, right? Times the height. In this case, the height, remember we said the height was the change in x? So both heights are the same. So really the volume, the difference is pi. I can take out the pi out, and this is really r big squared minus r small squared, and this is multiplied by the change in x. That's the volume of one washer. If I want to approximate the volume of the entire solid, so the approximate volume of solid, what would it be? It would be the summation of all these guys, wouldn't it be? So again, I'm doing this because I want you to see the connection between the Riemann sums that we talked about with integrals. So the idea is that I get a whole bunch of these, right? I get not just one disk, I get a whole bunch. I get a whole bunch of these washers and add them all up. But what do I do with them? I make it go to infinity, because to find the exact volume of the solid, I must make the limit go to infinity. That's why the limits are so powerful, because with this now, and my little knowledge of Riemann sums, I know that if I take this limit, what do I get? I get the integral from a to b of the inside function here, right? Well, this inside function here is pi multiplied by r big. What's r big? R big was what? 5 minus x squared. So this is 5 minus x squared. And this is squared minus the radius of the smaller one, which is 1/4 x squared. And this whole thing is dx. You see that? Now pi is a constant. I can take that out. A and b are what? I can specify a and b. They're -2 and 2. Right? That's my point. That's my bounds of integration as I found it. -2 and 2. And then I have to expand everything. So then I get what? I get 25 minus what? Minus 10x squared plus x squared, pardon me, not x squared. This is x to the fourth. And this will be minus x squared over 16 dx. Is everyone with me so far? Is everybody with me with the setup of the integral? Somewhat. So Moses, tell me what is it that is not clear?
The part where you were explaining the limit again around the exact volume of a solid. You
Correct.
can
So do you agree with me? Do you agree that what we figured out here is the volume of one of those washers? Is that clear?
uh yeah, I understand that part.
Okay. And do you agree with me that the idea is that I get a whole bunch of these washers and add them together to give me the approximation of the volume of the solid? Do you agree with that?
Yeah, and then because it's like a Riemann sum, you have to find the limit to infinity.
So the idea is that I get these washers, right? And I make them as thin as possible and fit an infinite number of them.
Okay, so kind of like area under a curve from like earlier.
That is correct. This is the step up, right? So when we did earlier was we found the rectangles, we made them as thin as possible and fit an infinite number of them, and then that became the exact area. In this case, we're taking an infinite number of volumes of washers, of cylindrical of cylinders that have holes in them. We're taking a whole bunch of them and we're making them go to infinity. And then that produces, this is exactly what integrals are. Do you understand? Integrals are just an infinite sum, because this is an infinite sum. But the it's like kind of magical because the thicknesses of these disks, they become really, really thin, infinitesimally small, infinitesimally thin. which is really hard to understand. That's why we abstractly think about this. So is that better?
Yeah, it makes a lot more sense now that you put it that way. Thanks.
Okay. Oh, and Justin, yes, you're right. I just saw that myself. So thank you, Justin. So this should be squared, and this should be to the fourth. Sorry, pardon me. This should be to the fourth. And then we can combine like terms here. We can combine like terms. So then you get pi integral from -2 to 2 of 25 minus 10 x squared. And then this is can be written as 16 over 16. Subtract 1 and you get plus 15/16 x to the fourth. So this is my integral. And what do you notice about my integral? My bounds are symmetric. And this function inside here is even. I can only do this if my function is even and my bounds of integration are symmetric. I can rewrite this integral as I could take out the 2, put it in front. The integral now goes from 0 to 2 instead, from -2 to 2, because I don't have to worry about that because it's even. 25 minus 10x squared plus 15/16 x to the fourth dx. And now from here, find the antiderivative. So this would be equal to 2 pi. The antiderivative would be 25 minus 5, no, pardon me. This is 10 thirds x cubed plus, this would be 15 over 16 times 5 x to the fifth power evaluated from 0 to 2. This should be 25x, pardon me. Okay, then I can plug stuff in and I get 25 times 2 minus 10 over 3 times 2 cubed plus. Now the 5's here cancel. This is really a 3. So this is 3/16 times 2 to the fifth power. And I don't have to plug in anything for the 0 because zeros just cancel everything out. So I don't have to worry about that part. This would be 2 pi multiplied by 50 minus, this is what, 10 times 8 over 3 plus 3 times 32 over 16. So this is 80 over 3. This is the 16 goes to the 32 twice. So this is really 6. This is 50. Okay. And then you can combine, this is 56 minus 80 over 3 times 2 pi. And what is that? You can write this as 2 pi multiplied by, so you have to multiply this by 3 times 56 over 3 minus 80 over 3. And then what would you get? You would get 8, 1, you get 168 over 3 minus 80 over 3. And you get 2 pi multiplied by 88 over 3. So this would be 176 pi over 3. Is that right? Let me just find the decimal expansion of this. This is 176 pi divided by 3. And that is correct. Everybody with me? So this is 184.307. And if you don't believe me, good thing we have Maple. And what does Maple say? Maple has this integral here, which is very much what we have, but I don't know where that e comes from here. Oh, because it's probably like truncated here. And then this is the exact volume of the solid. So we pretty much got the same thing. Okay. So then So then how can we what is the general rule then for the washer method? What is the general formula for washer method? So again, I would have two graphs, right? I would have some graph here and some graph here. Let me put this the other way. I would have some graph here and another graph here. And then I want to find what would happen if I take a region in between and revolve it around the x-axis. What would happen? How would I figure out that volume? So the idea is that I can find the volume of the solid and let me call this y equals f of x and y equals g of x. The idea is that if I revolve it, right? If I revolve this, I'll get something like this, right? I would get something like kind of similar to this. Something like this, right? And then I can figure out a washer whose radii is dependent upon the upper function and the lower function. So then I would say that the volume would be equal to the integral from a to b. You would have a piece of pi there, and you would take the upper function, which will represent the radius, square that minus the lower function g of x, and square that. So this is where that formula comes into play. So what I'm doing is I'm trying to give you guys the understanding of why the formula is what it is. I could have just said, hey, you know what? This is the volume formula using the washer method, and let's move on with our lives. But hopefully now when you see this formula, you start to see that there's a reason why we have what we have. There's a reason why we're squaring f and there's squaring g, because this represents the radius of this washer, which represents a cylinder with an outer radius or bigger radius and a smaller radius. And the outer radius is represented by the larger function and the inner radius is represented by the lower function. So that's the washer method. Does that make sense? So we talked about the disk method last lecture, and now we're talking about the washer method, which is really just an application of the disk method twice. We're taking the outer disk and we're subtracting off the inner disk. That's another way to think about the washer method. Okay? Okay. Now, what if I get something like this? I want to find the volume of solid created by revolving region bounded by what? Y squared equals x and x equals 2y. And I want to take that region and revolve it bounded by 1 and 2 about the y-axis. So first thing I want to do is I want to sketch, right? So one thing that would maybe help us first is to find the points of intersection. That usually is a great way to start. So points of intersection, I want to set. So if you look at this, I got y squared equals x, and I got x equals 2y. So I can set these x's equal to one another, which would mean that y squared has to equal 2y. So if I set it equal to one another and I can solve it, I get y squared minus 2y equals 0. Factor it, I get y minus 2 equals 0. So then I say I get that y equals 0 and y equals 2. So if y equals 0, what is x going to equal? If y equals 0, x equals 0. And if y equals 2, what is x going to equal? If y equals 2, then x equals, what does x equal? X equals 1/2? No, y equals 2. So y is going to be placed here, right? Into one of the equations I can figure out. That's right, Justin, it's 4. So then this would be 4. So I have the coordinates. I have the coordinates. The points of intersection are going to be 0, 0, and 4, 2. Do you see that? Okay. So then 0, 0 is one of the points, and then 2, 4, 2. 1, 2, 3, 4, and 1, 2. So that's going to be my other point of intersection. So I established the point of intersection. Now I want to give just a sketch. What is y squared equals x? What does that look like? What is y squared equals x going to look like? It is going to be a parabola, but where is it opening up? Is it opening up upward, downward, to the right, or to the left? To the right. That's right. That's right. So I'm going to have something like this. Right? This is y squared equals x. Or in other words, x equals y squared. It's an upward, it's a it's a parabola that's opening to the right. And then what is x equals 2y going to represent? Well, I can rewrite this as y equals 1/2 x, right? And I know what that is. It's a straight line that crosses through the origin whose slope is 1/2, rise over run, right? Goes up, goes up 1/2. So then I would have this as my graph. Let me draw this again. So this is y equals 1/2 x. Now what do I want? And let me just, for the sake of just this problem here, I'm going to make this a little bit more exaggerated. I'm going to exaggerate just a bit more. Okay. So what do I want? I want to take the region bounded between these two graphs. And what is that region? It's this one here. It's this portion here, right? But what do I want to do? I want to revolve around the y-axis. So then I'm going to get something like this. I'm going to get something like this. Let me use the same colors here. Right? And I'm going to have something like this. Right? Makes sense? Let me see if I can make this a little better on this guy. So the upper function here would be the square root of x. And the lower function would be 0.5 times x. And I'm going from 0 to 4. And the vertical axis is what's going to happen here. So you see, this is the piece that I get. Do you guys see that? This is the slither that I want to revolve around the y-axis. And when I do so, look what happens. You see that? I get like a cup, a weird cup this way. And then what am I going to do now? I'm going to cut it up. I don't know if you see it. Yeah. So you see these partitions? You see this? These are all the washers. You see that? These are different kinds of, this is what the shape would look like if I were to cut it up into horizontally speaking. You see that? Cool, right? Yeah, it's hollow in the middle. That's right. So that's why we call it washers, because they are not solid cylindrical discs. They have a hollowness in them. And because of that, what we're gonna do, of course, you can you can tell my drawing is not even remotely close uh, to giving you that three-dimensional feel. But the idea is that my washers, right? My washers here look something like this. Oh my goodness. This is not hard. This is not easy. So this is my washer. Do you see that? My washer has a smaller radius and a bigger radius. So then what's going to be the volume of the solid that I produce? Well, I'm going to have a certain integration bounds of integration. But the difference is that the disks are not going horizontally, right? They're not being stacked horizontally. Whereas in this scenario, my disks are horizontally stacked. They're sliced vertically, but horizontally stacked. In this case, my disks are what? Horizontally sliced, but vertically stacked. So then my integration bounds are not going to be the x interval, it's going to be the y interval. So my lower y value would be what? 0. My upper y value would be what? Where do they intersect? They intersect at 4 comma 2, right? So my upper y value would be 2. And then what do I write this? I write this as pi being outside, right? Remember, we're going to use the washer method, but the difference is that I'm going to look at the outer radius from a horizontal perspective. So what's my horizontal radius? Or what is the furthest function from the y value, from the y-axis? What's the furthest function away from the y-axis? Is it the blue or is it the blue or is it the pink? So again, I'm going to be taking the radius that's big, squaring it, minus the radius that's small, and squaring that. And this will not be in dx, it will be dy because of this reason. So it is the pink. It is the pink, guys. According to this, right, the distance from here to here is longer than the distance from here to here. So the distance from the center to the outer pink, which would be so the distance here. So I'm gonna draw this out here. Very rough sketch, guys. Very rough. This is y, right? And the pink is out here. and the blue is in here, something like that. And then this distance here represents the r big. So what would be the radius expressed as? This will be a radius will be expressed as a function of y, not a function of x. So then that's why we use this formula here. X is equal to 2y. So that's going to be my big radius, 2y. And then what's going to be my small radius? Smaller radius. It's going to be this distance here. And the smaller blue, right, is given by y squared equals x, or x equals y squared. And again, I want my radius, my radii to be functions of y in this case. So this will be y squared instead. So now I have this formula here, now I can plug in. I can get this as pi from 0 to 2. The radius the big radius is 2y squared minus the small one, which is y squared dy. Does everybody see the difference here? We're using the same idea that we've used for the previous example, right? Where we find the radius of the big one, subtract the radius from the smaller one, right? The difference is that the radii here are functions of x, but the radii here are functions of y. That's the only difference. And that might be sometimes a big difference for some, but that's the difference. Can you repeat the r big and r small part and why the function is changed? Okay, so yes. So I just want you to see, you guys are comfortable with finding the washer method when we slice vertically and stack horizontally, right? You guys are comfortable with representing the radii as functions of x, because my washers, right, the radii are functions of x. The difference here is that my cylinders, or my washers, are sliced horizontally. So the radii of each of these circles here, right, the radii are different, and they depend upon the not functions of x, but in this case they're functions of y. They as you get bigger and bigger, right, the radii changes. But how do they change? They change with respect to y. I know it's a little hard to understand. How do I say this? So as you stack up the washers, right, what's being changed? You're placing them on top of one another vertically. So for every change in the vertical position, right, your radii gets either bigger or smaller, correct? So that's why it's a function of the y values, as opposed to the function as the radii being functions with respect to the x values. Because in the other problem, right, in the other problem, my disks were being stacked horizontally, which means that the radii depends upon where that disk is stacked, what x value that disk is at. Do you understand? But now we don't care about the x value so much as opposed to the y values, because we're stacking them now vertically upon one another. So for every additional disk, right, my radii will be different with respect to y. So that is why, in this case, the radii is based upon functions of y. So the outer function here, right, the outer function is the function to the rightmost, to the axis of um, revolution. So I know there's a lot of things to keep in mind. So one thing we have to keep in mind is, what axis are we revolving about? Are we revolving about the y-axis or the x-axis? That's huge. So we're revolving about the y-axis. So that's one thing. So then the volume that I get is much different than if I were to take the same region and revolve it around the x-axis. So we're going to do the same thing here. We're going to do two things. We're going to do the revolution of the solid around the y-axis, and then see how it's different from the revolution around the x-axis. And then hopefully that will clarify all of this. But the r big, right, is represented by the bigger radius is represented by the function that's furthest away from the axis of revolution. And in this case, the pink here is the furthest away from the axis of revolution compared with the blue one in this region. We're only considering this region, so we don't really care about the rest. We don't care about the rest. We just care about in this region, which one is farthest away. That's it. So let me make this a little bit clearer here. Which one of these colors are farther away from the axis of symmetry, axis of revolution? Obviously, it's the pink, right? So we're going to make that our radius, the bigger one. And then which one is the smaller one is the one that's closest to the axis of revolution, which is the blue. And then how do we represent that radius? Well, we represent it as 2y because that's what it is. X equals 2y. X equals 2y is exactly what this line is. But we're writing it with respect to y, not x. So we solve for x. We're already given that here. So x equals 2y. X is a function of y. So r is going to be a function of y, 2y. And then what's going to be the smaller radius? It's going to be the blue one. It's a function of x, a function of y as well. So we're looking at it from the other perspective, guys. I know that's a little tricky, but we're saying x is equal to a function of y, which in this case, x is equal to y squared. So we're going to write this as y squared instead. Okay? I don't know if that made it more complicated or did it clarify? Did it clarify it for you a bit? Yeah, it takes some time. It really does. It's not something that you just like, oh, it just works out. You have to look at two things from two different angles. So we're so accustomed to seeing things as functions of x up until now. Now we have to make that switch. We have to be able to see things as functions of x and at the same time as functions of y. So being a function of x is not special. It doesn't have to be a function of x. It's just we're just ingrained in that way up until now. Now we don't have to worry about functions of x or functions of y. We can be anything. Okay, so now if we understand that, if we understand the differences between the radii, the smaller one and the bigger one, then the following should follow easily. Because now I have an integral that I should just have to integrate. So this is pi from 0 to 2 of 4y squared minus y to the fourth dy. What's the antiderivative? This will be 4/3 y cubed minus y to the fifth power over 5 from 0 to 2. This becomes 4/3 times 2 cubed minus 2 to the fifth over 5. This is 4/3 times 8 minus 32 over 5. This becomes what? 32 over 3 minus 32 over 5. Then we can make them the same denominator. So this will be 15 minus 32 times 3 over 15. And then we can write this as 5 times 32 minus 32 times 3 over 15. I can factor out the 32 and I get 32 times 5 minus 3 over 15 pi. This becomes 32 times 2 over 15 pi, which becomes 64 over 15 pi. So all I did was I just computed, okay? I just computed and I used the fact that I can factor things out. So I can simplify my computing. Normally people would from here, right? They would multiply these numbers and then subtract. But then I realized both of them have 32s in them. So then I don't have to really find what these are because I can factor out the 32. And I'm left with just saying 32 times 2. So it's just an easier way to compute. And that would be my final answer. And if I put this in my calculator, let me just see what I get. So I get 64 pi divided by 15, and I get 13.404, blah, 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 right? 13.404, dot, dot, dot. So let's see what Maple tells us. So Maple says right here. So if you notice, their integral is much different set up the way than what we did. So what Maple does here is something called the cylindrical shell method. So there's different methods to find volume of a solid. We're only going to be discussing two of them, the disk method and the washer method. If you continue in the book, the next page, the next section after this is the cylindrical shell method, and that's what they use for, that's what Maple uses for this. But still, it doesn't matter. We get the same numerical value. Okay. So that's if, this is if I revolve my original region, right? Look at my original region. That's if I revolve this region around the y-axis. That's the volume that I get. So we're all in agreement with that, right? Now, what's the difference if I revolve this region around the x-axis instead? So that's when I would change the line of revolution. You see that? I changed the line of revolution. And let's see what, I still get the same region, but look at the volume now. No, but look, Tassif. Now look, I still have to use the washer method, but it's going to be set up differently. Do you see that? Hold on, let me see if I can. Do you see how originally, so if I go back and forth, look, I can go back and forth. This is what I have to revolve it around the x-axis. What if I revolve it around the vertical axis? What do I get? I get this. Do you see this? It looks similar, but it's not the same. You see that? The region is exactly the same, guys. The region hasn't changed, but the solid becomes different. Do you see how this one here, this is like a cone? You see how this is like the straight cone here, and then you have like the inner part being curvy. But if you do it the other way, if you do it horizontally, revolve it, then it's not a cone. It's like a almost like a parabola. You see, this is a parabolic shape, and inside is the straight cone part. Do you guys see that? So yeah, so then our big switches exactly. So then now it's different, guys. Now look at the discs. Look at the discs. The discs are, look, do you guys see what I was saying now? The discs are sliced vertically but stacked horizontally. Whereas if I do it the other way, the discs or the washers that I have are sliced horizontally but stacked vertically. Do you see why I'm saying this now? Do you see the difference? The washer method hasn't changed. It's just that the washers themselves are different. And seeing that difference accounts for why the integrals will be different when we calculate it. So why don't we find the volume? So I'm gonna take the same region, guys. I'm gonna take the same region that we just found here, right? This is the region. All we care about is this region. In this case, I revolved it around the y-axis and I got this weird thing that I can't even draw. And then I'm gonna take the same region now, and you know what? I'm gonna say, forget about the y-axis. I'm gonna say, what if I revolve this around the x-axis? What would I get? So let's do that. So I'm gonna do the exact same thing here. I'll copy this. I'm gonna paste this. Now the only difference I want to change now, the only thing I'm gonna change is I'm gonna change this. I'm gonna say, how about the x-axis instead? So again, the graph is very much the same. I already know that at the intersect, right? I already know where they intersect. They intersect at 0, 0. And this is 1, 2, 3, 4. This is 1, 2. This is y, this is x, and I know that they intersect here, right? And I already know, oh, yeah, I just noticed that right now. Thank you. So all I'm doing now, I'm taking the same exact problem that we had here, where we took away the region. We took this region and we revolved it around the y-axis. I'm taking the same problem, but now instead of revolving it around the y-axis, I'm taking the same region and revolving it around the x-axis, and we'll see the difference. So we already know what it looks like, right? We already know that this is the blue portion here, and this is the red portion here, right here. And we know that this is y equals 1/2 x, and this is y squared equals x, right? We know this, right? But when we revolve it around the x-axis, what do we get? As we saw in using Maple, we saw this, right? Right, we saw this. And now what else do we see? We saw that the discs here, right? My discs are being sliced vertically, but being stacked horizontally. And then with that in mind, the big radius is no longer going to be the pink one as we had it for the other example. The bigger radius is the function that is farthest away from the x-axis in this region, of course. And that r big, right? The r big would be that blue graph. And then the smaller one would be the smaller radius. So let me just make that a little bit clearer here. So big here, what is r big? R big is the function that's above the pink one, which would be what? Y squared equals x. Now, what's the problem here? The issue for all of these radii stuff, right, is what is it? What kind of function is it? Is it a function of x or a function of y? So when we cut them vertically and we stacking them horizontally, our radii are functions of x because it depends upon where the disk is at horizontally. It depends upon what the x value is. So depending upon the x value that I'm at, it's going to affect what my y value will be. So my radii are going to be functions of x. But do you see what's the issue here? I have this y squared equals x. That's not a function of x. So then what do I have to do? I have to solve for y. And what does y equal to? The square root of x. That's all. So then the big radius will be square root of x. Do you guys see that? Now what's the small one? R small. It's going to be the smaller radius. And that's going to be associated with the pink function, which in this case is 1/2 x. It's already defined for me. I was able to figure it out already. Y is a function of x. So this is going to be 1/2 x. And then what would be how do I set up my integral now? What would be the setup? What would be the volume of my solid? It would be pi, and I'm integrating from what to what? So my bounds of integration are different, right? They're dependent upon the x values. So where am I arranging my x values in this region here? Four and zero. Yeah, it's going to be 0 and 4. So this will be 0, 4. And then my big radius is going to be square root of x, and I square that minus the small radius, 1/2 x, square that, and that's going to be dx. And now I have a different formula. Now I have a different integral. So square root of x squared is x. 1/2 x squared would be 1/4 x squared. And this is from 0 to 4. Then the antiderivative, pardon me, the antiderivative would be x squared over 2 minus 1/12 x cubed, evaluated from 0 to 4. Then I can plug in the 4, I get 4 squared over 2 minus 1/12 times 4 cubed, and I get 16 over 2 minus 4 cubed is 64 over 12. I can divide by 4, and I get 16 over 3 minus 16 over 2 pi. And then I can write this as pi times, this will be 3 times 16 over 6 minus 16 times 2 over 6. And then what would I get? I would get 16 over 6 pi, which reduces to 8/3 pi. And what is 8/3 pi? 8 pi divided by 3. I get 8.377. 8.377 dot 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 dot. That's my volume. Is that clear? Any questions about this? So hopefully the integration part of it, right? All of these steps here are not the hard part, because we've been doing more complicated functions. So this part usually is the easier part of this. The harder part is setting up the correct integral. That's really the key here, setting it up. There's a lot of prep work here behind this, right? You have to figure out what is the correct outer radius or the bigger radius, what's the correct smaller radius, how do we express it correctly so that we can plug it in the formula so that we get the answer. And then just to verify, let's see what Maple says. Maple says it's exactly, the volume of the solid is exactly 8.377, which is the approximation of 8/3 pi. So when we revolve this region, when we revolve the region around the x-axis, this is what I get. This is the solid that I get. Okay. And my volume was 8.377. And if I revolve it around the y-axis, this is the new solid that I get. And we got 13.404. So do you guys see the difference now between using the washer method when you revolve around the x-axis as compared to using it when you revolve it around the y-axis? Does that make more sense now? Oh, so for the most part, Ileana, I don't necessarily want to see the for these kind of problems, I don't want to see the rounded answer. I want to see the simplified exact answer. So this is really the one that I want to see. I want to see this. So this is exact. See, this is an exact answer because it's exactly 8/3 pi. But this here is an approximation. And oh, sorry about that. So this is what I meant to say. This is the exact answer. This is what I want to see for the final answer if you talk about an exam. Because this is exactly what it's supposed to be. It encapsulates exactly what the value is. But this would give you just the approximation. It won't give you the exact answer because it's an irrational number. Okay? Okay. Great. Great. All right. Now, we have a few minutes. Now, what I want to do is now, what's so special about revolving a region around the x-axis and the y-axis? Do we always have to revolve around those two axes? Can we use another axis? So the answer is yes. It doesn't have to always be x-axis or the y-axis. It could be some other line. So that's when it gets interesting. So let's see that. So this is when the solids of revolution do not occur around the x-axis nor the y-axis, but on some other axis. So let's see. So let me give you this. So what if I get y equals square root of x and y equals x, and revolve region bounded by these two functions about the line y equals 1. So this here is the new axis of symmetry. So now the question is, what happens if my, why do I say axis of symmetry? Axis of revolution. It's no longer the x-axis and no longer the y-axis. But again, the idea is the same. So let's draw this. Let's draw the region first. Well, what do we know about these two functions? What if we want to find the points of intersection first? This is rather easy because y equals square root of x, y equals x. We can say that x equals square root of x. Then if we want to solve this, what would we do? We would square both sides. We get x squared equals x. Then we get a quadratic, x squared minus x equals 0. So x minus 1 equals 0. So then we get that x equals 0 and x equals 1. These are 2 points of intersection. So I got x equals 0. I got 1. Right? And when x equals 1, y equals 1. So I have these 2 points of intersection. I got this, and I got this. And then y equals x is just going to be the straight line here. And again, I only want to know about this portion here. Let me make this straight. And then square root of x will be this. So again, it's pretty much the same kind of region that we had before. And I want this region, right? I want this region. Now, normally, what would we do? We would take this region and revolve it around the x-axis, right? That's normally what we would do. Or we would say, hey, revolve it around the y-axis. But we're not going to do this anymore. Now we're going to revolve it around the y equals 1. Now y equals 1, where is y equals 1? This is my new axis of symmetry, axis of revolution. I'm going to revolve it around this line. So do you see what's the result? Do you see what kind of shape we have now? Do you see this? Do you see now how I can create new solids based upon new axis of symmetry? It doesn't have to be the x-axis nor the y-axis. It could be any line. This is one of them. And you see how we have to apply, do you see how we have to apply the washer method because of this hollowness inside? So then the question becomes, I want to find the volume of this new solid. I want to find the volume of the solid. What's going to be the volume? It's going to be pi from what to what? Well, in this case, because of the solid is revolved uh, about a line that's horizontal, right? That means that I'm stacking my discs, my washers horizontally. I'm slicing them vertically, but stacking them horizontally. So it's going to be the x values that I care about. So it's going to be 0 to 1. Now the question becomes, the big question is, what is the bigger radius? What is the smaller radius? That's really the crux of all of these problems. If you can do that, then you're going to solve 95% of these problems. It's just figuring out two things. What are the integration bounds? One. Two, pardon me, what are the radii? If you can do those two things, then you're golden. So what would be the big or the larger radius? How would you express that? Y equals x. So be careful. You know what y equals x represents? This is what y equals x represents. That's not the big radius, right? The big radius is what? Is this. So look at this as my center. And look at this. This is the outer one. You see that? So then how do I express this distance here? Y equals x. Y equals x is this. So what do I do instead? This is the tricky part. If you get this, then we're off to the races. Do you understand? If this is x, for example, right? Then what's the y coordinate going to be? It's also going to be x, correct? But that's not the radius. The radius that I'm considering is what? Is this portion here to here. So then what is this with respect to x? So think about it. If this is 1 away, right? If this whole thing is 1 and this portion here is x, then what is this portion going to have to be? Anybody? It's going to be what? No, it's not going to be 1/2. Not 1/2. Say it again. Okay, so you see, this is when things get a little more complicated. So we are so accustomed to revolving around the x-axis or revolving it around the y-axis, correct? Now we're not revolving it about neither of those two axes. We're going to revolve it around another axis. And we're going to call that axis, in this case, y equals 1. We're going to make y equals 1 our new axis of revolution. This region is a particular kind of region. And we're going to revolve it around y equals 1. So we get this kind of shape, right? The hard part of this kind of problem is to figure out how do you express the bigger radius of one of those washers. Now, someone said y equals x is the outer radius, but that's not the outer radius because our axis of revolution is no longer the x-axis, it's y equals 1. So my center is this. This is my center, correct? And how do you figure out the radius? You find the distance from your center to the outside, correct? So I'm looking for this distance here. I'm looking for this. I'm not looking for this. This would be correct. This would be the inner radius if I were to revolve this around the x-axis. This would be the inner. But I want to find this. So this is very simple algebra. If this entire thing is 1, and this portion here is x, because that's what it is, y equals x. So y is equal to x. So if this is x and this whole thing is 1, then what is this piece here going to be? 1 minus x. Perfect, Samantha. That's right. It's 1 minus x. So it's going to be 1 minus x parentheses squared. Now subtract that from the smaller radius. What's going to be the smaller radius? It's going to be this here. It's going to be where the center, right, goes right to the blue. That's going to be my inner radius. So this is going to be a smaller radius, right? So I'm going to do the same exact thing. I'm going to do what? No, it's not going to be rad x minus 1. It's not. Think about it again. Think about it again. This whole thing is 1. This whole thing is 1. And this portion here is rad x. So then this portion here would have to be 1 minus rad x. So what I would say to you guys is to go back and understand this a little bit more as to why these are the scenarios that they are. It takes a little bit of time to see, oh, that's why it is. So this is 1 minus x squared, rad x squared dx. This would be the integral. And so let's do this real quick. We call it a day. So it's going to be 1 minus 2x squared, 2x plus x squared. And this is minus 1 minus 2 rad x plus x. Dx, this would be 1 minus 2x plus x squared minus 1 plus 2 rad x minus x dx from 0 to 1 of pi. So the ones here cancel. The negative 2x and the minus 2x becomes minus 3x plus x squared plus 2 rad x. And I'm evaluating this from 0 to 1 dx pi. Now the integral is going to be negative 3 over 2x squared plus x cubed over 3 plus this is going to be 2x to the 3 halves over this will be 4 over 3. And evaluate that from 0 to 1. And this becomes pi. Plug in 1 and you get negative 3 halves plus 1/3 plus 4/3. And if I plug in 0, I get 0 for everything, so I don't have to worry about that. Now make them all the same denominator, and I get negative 6 over, sorry, no, negative 9. Negative 9 over 6 plus, this would be 2 over 6 plus 8 over 6, right? Pi. And this will equal pi multiplied by 1 over 6. Because 2 plus 8 is 10 minus 9 is 1. So it'll be 1/6. So it'll be pi over 6. And just to make sure we're okay, we take pi divided by 6. We get 0 0.5235. 0 0.5235. Dot, 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 dot. So again, hopefully after you set up the integral, the integration steps are the easier parts for you guys. And let me just verify this with Maple. So again, what's our upper function, or what's our function? Our upper function here would be the square root of x. Doesn't really matter here, and this just becomes x, right? And it goes from 0 to 1. I'm just gonna calculate for you the region, and you see this, the line of revolution is gonna be horizontal, and the distance is gonna be 1 because y equals 1. So if I look at the region without the volume, this is what I have, right? But I'm revolving it around the y equals 1. So when I do that, this is exactly what I got. Remember this? This is exactly what we got. And then look at the answer. It's 1 pi, 1/6 pi, 0.5235. So the hard part, guys, the hard part is not the calculus anymore. The hard part is the geometry. In particular, it's the algebraic, it's the coordinate geometry behind it. If you understand the coordinate geometry behind this, then these kind of problems are not so hard. But if it takes some time, you have to just consider, why is that the big radius is 1 minus x, and why is that the small radius is 1 minus square root of x? Why is it? If you understand that, then you're good. Okay, so any questions about this? Does anybody have any questions about the big and the small for this problem? Does everybody see why the small is 1 minus square root of x? Does everyone see that? Yes. Okay. All right, guys. Yes, good. You're gonna have to revolve your head around this more. Haha. Boom, boom. That was I wanted to use that one. All right. Have a good weekend, guys. Yeah, Samantha, R big would be the one furthest from the axis of revolution. That's right. That's right, Samantha. The biggest radius, the bigger radius is is represented by what's farthest away from the axis. So that's why it's so important to understand what's my axis of revolution. So in this case, my axis of revolution is y equals 1. So that's my center. And that's why the pink is farthest away. In this scenario, if my axis of symmetry, however, revolution was the x-axis, the pink would be the closest. So it's all about it's all about the perspective. Where do you view it from? What's your perspective? Okay. Yeah, and David, I will email you all the topics, and for the most part, um, it's gonna be what we discussed after the exam, which are volume. Okay.